Hello, everyone. We're going to go ahead and get started on section 4.3, which is on logarithmic functions. So as an overview, logarithmic functions are the inverses of exponential functions. So we just learned about exponential functions. Logarithmic functions are their inverses. And we learned about inverse functions back in chapter 2. We want to recall that when we defined inverse functions, we said that only one-to-one functions had inverses. Therefore, exponential functions are one-to-one and they have inverses. So this means that logarithmic functions are also one-to-one, since their inverses would be exponential functions. So we see that they're inverses of each other. If we look at our image here, we see that we have y is equal to a to the power of x. This is an exponential function. And its corresponding logarithmic function will look like y is equal to log base a of x. And we'll kind of learn more about what this means later on. But we see that they are inverses since they are mirrored across the line y is equal to x. And here we just state that a is greater than 1. But so these are what our functions would kind of end up looking like since they're inverses. But so solving logarithmic functions utilizes algebra or a calculator, depending on the difficulty level and specific types of criteria. So we're going to kind of be switching in between, using algebra to solve logarithmic problems and also using calculators. So starting off, the definition of logarithmic function, we let a be a positive number that does not equal 1. Same thing for exponential functions. The logarithmic function with base a denoted by log base a. That's how we say it verbally as well, but we see the log with the subscript a. And this is defined by log base a of x, which is the same thing as saying a to the power of y is equal to x. So log base a of x is the exponent to which the base a must be raised in order to give x. So what we're looking at here for logarithmic functions, in a way, it's almost like a rewrite. We're rewriting exponential functions in this different format, which we call logarithmic functions. So when using the definition of logarithmics to switch in between logarithmic form and exponential form, it's also just important to note the base is always the same. So if we want something in logarithmic form and we want to put it in exponential form, we're given log base a of x is equal to y. A is the base, so that's the base of your exponent, the a that we see here. Then we see what log base a of x is equal to the exponent, the actual exponent y in this exponential form. X is the result. So we see log base a of x. The x is the actual result that your exponential form is equal to. So we kind of see that's how they're really just being rewritten. So exponential forms and logarithmic forms are really just rewriting. We're rewriting the functions, and the log part is the part that actually, calculates like new values. But as far as logarithmic and exponential forms go, it's a lot more of rewriting than anything. It's going in between logarithmic and exponential forms and rewriting those different equations. So that's going on basically like that definition of the logarithmic function. So let's go ahead and do an example. We want to evaluate the logarithmic function and then rewrite it in exponential form. So we're going to evaluate it and write it in exponential form. We see part A is log base 10 of 1,000. We want to know what that's equal to. And B, log base 16 of 4. We want to know what that's going to be equal to as well. So let's go ahead and go to our notes. So we see here for example 1, we've got part A log base 10 of 1,000 and B log base 16 of 4. So we're really quickly just going to rewrite this and show how we rewrite logarithmic versus exponential forms. So if we start with an exponent and we say we have a to the power of y equals x, like that, then when we rewrite it in logarithmic form, we write the word log every time, and the base is a. It was the base of the exponent. And then we're taking this log base a of the result of that value of x. And this is equal to the exponent, which we said was y. So when we rewrite it, we can rewrite it in this form. We're really taking the exact same numbers and putting it in the logarithmic form versus starting at exponential. But so we see that these numbers get replaced. These numbers get replaced. And these numbers get replaced. So they all get kind of like flipped around and switched. So for our example, for part A, we have log base 10 of 1,000. So 10 is going to be our base, and 1,000 is our result. And we don't know what this is equal to. Technically, we're really saying that this is equal to y, but we don't know what y is yet. So in our exponential form, this is going to look like 10 to the power of y is equal to 1,000. And lastly, we just really want to figure out what y is going to be. We need to figure out what value of y would have to be the exponent of 10 in order to give us 1,000. And that answer would be 3. So y, or our exponent, would have to be 3 to make this true, which means that log base 10 of 1,000 is equal to 3, while 10 to the power of 3 is equal to 1,000. So that's the result that we'll end up seeing. So now we're going to do the same thing with part B. We've got log base 16. Ooh, wrong one. We've got log base 16 of 4 is equal to y. So putting everything in the same format again, we're going to see 16 is our base. It's to some exponent y, and it's equal to 4. So we want to know, what is this value of y going to be? It's the exponent of 16. 16 to some power has to be equal to 4. Well, if we really think about it, the square root of 16 is 4. So we want the exponential form of a square root, which is 1/2. Something to the power of 1/2 is the same thing as saying the square root. So for part A, we got that y was 3. Its exponential form was 10 to the power of y is equal to 1,000. And for part B, we got log base 16 of 4. That was going to be equal to y, which was 1/2, which is also going to be the same thing as saying 16 to the power of 1/2 is equal to 4. So, all right, that wraps up example 1. Let's go ahead and head back over to our notes. All right, so that wrapped up example 1. We've got some properties of logarithms as well. So these are just going to be helpful properties to keep in mind as you work through problems. They're always true. They're always kind of the same. So it should be kind of go-to things that you think of if you happen to see them. So we've got log base a of 1 is always 0. So log base anything of 1 has to be 0, because this means that you raise a to the power of 0, and that would be 1. 1 is the result, 0 is the exponent. Anything to the power of 0 is going to be 1. So log base anything of 1 has to be equal to 0. Then log base a of a has to be equal to 1. So we are saying here that we must raise a to the power of 1 in order to get a. We said that a was the result, 1 was the exponent of the base a. So anything to the power of 1 is itself, is what we're saying here. Then 3 and 4 are basically the same. It's just that we've kind of reversed it. So 3 is taking the logarithm of an exponential function, and 4 is taking the exponential function of a logarithm. So same thing happens, but we kind of just flip the order there. But for part 3, we have log base a of a to the power of x. That just has to equal x, because we're saying that we have to raise a to the power of x in order to get the result a to the power of x. So we can always kind of rewrite numbers as well to try and make this work and try and kind of match this format. So we can just have that one value. So log base something of that something to a power is just going to be equal to that power. Because we're saying a to the x is the result. X has to be the exponent on a for that to be true. Then for part 4, we've got a to the power of log base a of x has to be equal to x. So since log base a of x is the power to which a has to be raised, that has to be raised in order to actually get the value of x. So 3 and 4 are, you're kind of taking the inverse of itself. You're taking the inverse. You're either taking the logarithm of the exponential function or you're taking the exponential function of the logarithmic function. So we see their inverses. That's kind of the properties for problems 3 and 4. Basically, you just want to be on the lookout for anything that could pop up that looks like that. All right, so moving on to logarithmic functions, we say that since logarithmic functions are the inverses of exponential functions, logarithmic functions will have the domain 0 to infinity. Or in other words, it's a positive domain that does not include 0. And it's the range of all real numbers. So we see its domain and range are flipped when it comes to logarithmic functions versus exponential functions. So if we look at the picture here, our exponential function is in blue and our logarithmic function is in red. And this is that line y is equal to x. We're seeing here that they're inverses, but also just looking at kind of generic exponential functions and logarithmic functions. So since our range of exponential functions are always 0 to infinity, that has to be the domain of the logarithmic function. That's because they're inverses. So the domain of the logarithmic function is 0 to positive infinity. Then the range would be all real numbers, since we see that the domain of the exponential function was all real numbers. Remember, they are switched for inverse functions. Since they're inverse functions, we switch domains and ranges. But that is kind of the point that we're looking at. Really, we're trying to say that domain has to be positive and not 0. So we're excluding 0, but domains always have to be positive. So we're seeing that kind of come up again here. When we worked on domains before, we said like domains of square roots had to be greater than or equal to 0. They are not related, but we are saying here that domains have to be positive. They have to be positive and not equal to 0. You cannot take a logarithm of 0. So that's what you want to remember. Cannot take a logarithm of any base, cannot take a logarithm of 0, which means that your domain has to be all positive values of whatever's kind of inside your parentheses for your logarithmic functions. We're got a problem like that next. And so logarithmic graphs, like obviously as we've seen before, can be obtained by reflecting the graph of its representative exponential function across the line y is equal to x. Or you can also obtain a logarithmic graph by creating a table of values and connecting the points with a smooth curve. Like if you just wanted to create a graph of a logarithmic function, you could just create a table of values, calculate points, plot those points, connect it with a smooth curve. If it just ever so happened that you wanted to somehow plot a logarithmic function yourself, that's what it would look like, as opposed to using like a graphic calculator. All right, so really kind of harping again on this domain has to be positive. Let's get into example 2. Example 2, we want to find the domain of f of x is equal to log of base 4 of x squared minus 9. So this is the problem that we're going to work on. So we're going to go ahead and head over to our notes. All right, so for example 2, we have log base 4 of x squared minus 9, and we're trying to find the domain. When it comes to domains of logarithmic functions, we're really saying that whatever is inside, whatever value we're using for this domain, it has to be positive. So whatever shows up inside these parentheses always has to be positive. So for our domain, we say we can only take logarithms of positive numbers, not zero. So not including zero. So if we want to find the domain of a function, we really just want to figure out whatever's inside the parentheses, when is it positive? That's where our domain is going to be. So it doesn't really matter what base our logarithm is. It could be log base 4, log base 10, log base 1,000, whatever. We cannot take a logarithm of a negative number, or zero for that matter. So this means that x squared minus 9 has to be greater than 0. And what we have there is a polynomial inequality. We've got x squared minus 9 greater than 0. So since this is going to be a polynomial inequality, we're going to go ahead. We want to solve this. So we can go ahead and factor x squared minus 9. X squared minus 9 is a difference of squares. So it factors into x plus 3 times x minus 3. We're stating that x plus 3 times x minus 3 has to be greater than 0. So our zeros in this case are going to be -3 and +3, which means our intervals will end up being -infinity to -3, -3 to 3, and 3 to infinity. So these are the 3 potential intervals that our polynomial can be positive on. So we'll make our little chart here. It won't be nearly as long as we saw some, because we only have the 3 intervals and then we have the 2 factors. So we've got -infinity to -3, -3 to 3, and 3 to infinity. And we've got x plus 3, x minus 3. And at the bottom here, we want to know, when is x squared minus 9 going to be greater than 0? So our x squared minus 9, remember, is like kind of the result as we go through some problems here. We can pick some test points if we want. We can say maybe this is -4, this will be 0, and this will be +4. We're going to fill in our boxes. So if we use the test point -4, if we say -4 plus +3, that's going to be still a negative number. Then -4 minus 3, that's also going to be a negative number. So that means that x squared minus 9, we have a negative number times a negative number, which creates a positive number. Then for 0, if we have 0 plus 3, that's going to be a positive number, that's 3. If we have 0 minus 3, it's going to be a negative number, which means that positive number times a negative number ends up being a negative number. So x squared minus 9 is negative on the interval -3 to 3. Then lastly, picking the test point 4 plus 3, that's positive, that's going to be 7. Then 4 minus 3, that's also positive, that'd be like 1. So positive numbers times positive numbers gives us positive numbers. So if we said we wanted to know when x squared minus 9 was greater than 0, it would be at these 2 intervals. So we see x squared minus 9 greater than 0 here and here. This means that for our problem, our domain of our function, since it has to be greater than 0 and not equal to 0, our domain ends up being negative infinity to negative 3 and 3 to infinity. So that would be the domain of our function. Now, once again, as a reminder, it doesn't matter what the base is. In this case, base is 4, base could have been 5, 3, 10, 100, doesn't matter. Just means that whatever's in those parentheses has to stay positive. In this case, we had x squared minus 9. We needed that to remain positive as well. So, all right, that wraps up example 2. So we are just going to take a really quick look at this function in Desmos before we head back over to our slides. But all right, so here is that function log base 4 of x squared minus 9. We put some vertical asymptotes in here at negative 3 and 3, just kind of get like a good sense of what's going on here. But yes, we see our function is only ever going to be defined for values less than negative 3 and also greater than positive 3, and neither one of those values. So none of the domain part, like in between, doesn't include those values that would make it equal 0, only for less than negative 3 and greater than positive 3. So this is kind of what, that function looks like when you've got something that looks like log base 4 of a difference of squares. This is what that function tends to look like. The chunk in the middle gets excluded, while the ones on the ends are the ones that are included. All right, well, let's head back over to our slides now. All right, so that wrapped up example 2. Continuing on with graphs of logarithmic functions. Once again, transformations from section 2.6 come back around. We say we can use these transformations to obtain graphs of other logarithmic functions, but we're really only going to do shifting and reflecting. Shifting and reflecting are the only transformations that you want to use when it comes to graphs of logarithmic functions. So with reflecting, we see it's either reflected about the x-axis, so giving that negative kind of on the outside, or it can be reflected across the y-axis, so plugging in that negative 2x specifically. Then we have shifting as well, so shifting up or down versus left or right. For that shifting, we're adding or subtracting numbers from the logarithm in order to make it go up or down. And then for shifting left and right, we're adding or subtracting those values directly from x inside the logarithm to shift them to the left or to the right. So these are the different types of transformations that we can see on graphs of logarithmic functions. Very similar to exponential functions. All right, so now we're going to talk about common logarithms. So the common logarithm is the logarithm of base 10. So it's called the common logarithm because it was used so often that it just became so common that people just got so lazy that they stopped writing the base 10 part. So that's why it's called the common logarithm. So if you just omit the base, like if you say log of x, that is inherently understood as log base 10 of x. So if you see a logarithm and there is no base there, it means base 10. You want to remember that. So your calculator actually automatically calculates logarithms as common logarithms. So on your calculator, there is a log button that is common log, that is log base 10. So it calculates the values using that log function as logarithms to base 10. So to calculate logarithmic functions that don't have base 10, some calculators can calculate logarithms that don't have base 10. I personally actually don't know how to do it, but I'm sure with a little looking online, you probably can. But if you didn't, then you would need to use algebra skills and your knowledge of exponential functions to get the correct answer. So you just need to kind of like fiddle around with whatever you're given to try and solve it. But common logarithms, they are logarithms of base 10. That is what is in your calculator. That is what the button log on your calculator will solve for you. So we're going to go ahead and do another example. We have a certain strain of bacteria divides every 5 hours. Yeah, 5 hours. If a colony started with 60 bacteria, then the time t in hours required for the colony to grow to n bacteria is given by t is equal to 5 times log of n divided by 60 over log of 2. Since we don't see any bases, this is log base 10. This is the common logarithm. We want to find the time required for the colony to grow to 3 million bacteria, rounding to 2 decimal places. So even though this equation looks, a little funky, a little strange, whatever, really we're just plugging this into our calculators. We're replacing n with 3 million and putting it straight into the calculators. So let's go ahead. We're going to head over to our notes real quick, just to kind of copy this down, and then we'll use our calculators. All right, so for problem 3, we have t is equal to the time for bacteria to grow, and n is the amount of bacteria after t hours. Our equation we said was t is equal to 5 times log of n divided by 60 divided by log of 20. We said that n was going to be 3 million, so we're going to go ahead and plug in 3 million for n, which means that this is equal to 5 times log of 3 million divided by 60, all divided by log of 2. Remember, common logarithms. So you kind of have 2 options. At this point, you could plug this number straight into your calculator. You could, divide 3 million by 60 and just kind of see what result you get. If you did that, you would get 5 of log of 50,000 divided by log of 2. Either way you go about it, you should get the same answer. We want to find the number of hours it's going to take to get to 3 million bacteria. So we're plugging this equation into our calculator and rounding to 2 decimal places. So let's go ahead and plug this into our calculators. All right, so here is our calculator here. We're going to go ahead and put this in. So we're going to start off by doing 5 times. We're going to be using quite a bit of parentheses probably in this case. So we've got 5 times parentheses, and then we're going to plug in our log of, we're going to go ahead, we're going to put 50,000, but you could definitely put your 3 million divided by 60. So we got 50,000 divided by log of 2. Close off those parentheses. This is what we're calculating. And boom, there we go. We got 78.04820237. We're rounding to 2 decimal places. So this is really going to look like 78.05. If you did want to put in 3 million divided by 60, you could absolutely do that. It would be almost the same. You would plug in, 5 times parentheses log of 3 million, so 3,000,000,000. There we go, divided by 60. Close off that logarithm, divided by log of 2. Close off those parentheses, and there we go. We get the same answer. So whichever one you decided to plug into your calculator, same answer would have come out either way, and you would have gotten that answer correct. So you want to keep that in mind. It's really just how well can you use a calculator. That's what you want to remember kind of about these sections that we've got going on here. So all right, let's go ahead and go write this answer in our notes. All right, so after using our calculator, we said that this was going to be about 78.05, and this is in hours. So this would be quite a few hours here. But that would be our answer there for problem 3. So it's really just plugging in that value for n and calculating the result. So all right, let's head back over to our slides. So we wrapped up example 3 here. So let's move on to natural logarithms. So we just talked about the common logarithm. Now we have natural logarithms. The natural logarithm is logarithm base e. This is the same e that we use for exponential functions. So logarithm with base e is the natural logarithm and is denoted by the letters ln, and we will call it ln. So ln of x is the same thing as log base e of x. This is another one that got used so much and so often that instead of writing log base e all the time, just changed it to ln of x. ln of x does not have a base. It does not have a defined base. So we see kind of the same thing where we saw log base e of x, but we don't have a base for the ln of x. It is log base e, so we don't need to write a base for ln x. And by the definition of inverse functions, we say that the natural log of x equal to y. This is the same thing as saying e to the power of y is equal to x. So this is the inverse of the exponential function. Remember, we called it the exponential function if it was base e. So this is the natural logarithm function. And the properties of natural logarithms have the same properties of regular logarithms. So the properties that we saw before, we have the exact same properties. We're still going to go over them, but we have the exact same ones. And your calculators come with an ln key, and this allows you to calculate natural logarithmic values. So that ln key will let you calculate anything log base e, the natural logarithm. Just like how we saw before, your calculator calculates the common logarithm, log base 10. It also calculates the natural logarithm, log base e, or just simply ln. So here are properties. Like we said, they are the same properties as before, but we're going to go over them anyway. Number one, the natural log of 1 is 0. Anything to the power of 0 is equal to 1. And remember, this natural log, it is equal to the exponent. So we raise e to the power of 0 in order to get 1. Then 2, the natural log of e is 1. Since the natural log of e is like saying the natural log of e to the power of 1, our answer is 1. We have to raise e to the power of 1 in order to get e. Then 3 and 4, just like before, these are kind of those inverse functions. We're kind of plugging one into the other and we get the answer of x. So 3 is taking the natural log of e to the x. 4 is taking e to the x of the natural log. So with 3, we have the natural log of e to the x has to be equal to x. You have to raise e to the power of x in order to get e to the power of x. So that's kind of how we reason out, number 3. Then number 4, we have e to the power of the natural log of x is also equal to x. The natural log of x is the power to which e must be raised in order to get x. It is equal to y, which is why we say that e to the power of y is equal to x. Natural log of x is y. All right, so these are all of our properties of natural logarithms. We're going to go ahead and do our last example. So example 4, we're going to evaluate the natural logarithmic functions. A, we have the natural log of e to the power of 167, and then for part B, we've got the natural log of 7. So I'm going to go ahead and head over to our notes to do this last example. All right, so here we are. Problem 4, we've got part A, the natural log of e to the power of 167, and part B, natural log of 7. So starting with part A, we've got the natural log of e to the power of 167. So what we're looking at here is the inverse function. Like, we're taking the function of itself. We're saying the natural log of e raised to some power. The natural log of e is log base e. So we're saying log base e of e to some exponent. The answer is always that exponent. So our answer, we don't even need a calculator for part A. We see the natural log of e. Immediately, the answer is whatever the exponent was. In our case, it was 167. So the answer was 167. So the log of e, or the natural log of e, They're inverses. So they cancel. They cancel each other out, and your answer is the exponent. So didn't need a calculator for that one. That was good. So for part B, we've got the natural log of 7. We're going to head over to our calculator to calculate this value. We do need to use a calculator to calculate this, so we want to make sure to do that. So let's go on over to a calculator. All right, we said that to put in a logarithm or natural logarithm into our calculator, we want to use this ln button that's right here. So we want to find the natural log of 7, so we're going to do ln of 7, close off that parentheses, and there we go. The answer is going to be 1.945910149. We're just going to round this to a few decimal places in our notes, just get the point kind of going on here. But this would be how you'd calculate a natural log. The natural log is using the natural log button and then plugging in whatever you want to evaluate inside your parentheses here to get your answer. So once again, how well can you use a calculator? That's what this section's all about. So let's head on back over to our notes just to write down this answer. All right, so from our calculator, we said this answer was 1.945910149. You don't have to write that many decimal places. However many decimal places really depends on the question being asked, like in WebAssign. You would have to round to that many. Just for safety's sake, we'll make it 5 decimal places. I think that actually might be one of the types of like rounding they ask for. So we'll round to 5 decimal places. This is going to end up being 1.9459 and 1. So there we go. Those are our 2 answers for that last example, example 4. So let's head on back over to our slides. All right, so that finished up example 4, which wraps up section 4.3. So in section 4.3, we learned about logarithmic functions, graphs of logarithmic functions, common logarithms, and the natural logarithms. So all right, that wraps up all of our lecture videos. So when we get back into class, we'll be able to jump right back in with section 4.4. So all right, everyone, if you have any questions about any of the lecture videos that we created, and have a great day, and I'll see you all in class.